Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. In this video we are going to display the progress of importing items. In addition, we'll implement coalescing meshes, which allows the user to save multiple meshes into the same asset file. In the last video, we made this importing items visualization and integrated it into the editor. The only part that's not plugged in yet is the import progression. In order to do this, we have to somehow pass the progress maximum and its current value from the importer to the editor. I'll set it up in the C++ side first. In Content Tools project, we can add a new class in the Tools common header file. Here we define a function pointer type for any function that takes two signed integers. This is the signature of the function that we call back every time the progression value needs updating. We set this function pointer through the constructor of this class. We don't want multiple copies of an instance to exist, so we disable copy. Progression value and max values can be updated using the callback member function, which also calls the callback function pointer if it's not null. We can also get the value and max value using these accessor functions. Now we can use this to pass progression values. I'll fix my typo here first. In process scene, we'll add a new parameter which is a pointer to an instance of progression class. In the implementation, we passed this function pointer to any other function that needs to update progression. In addition, we increased the progress value after processing each mesh. In split meshes by material function, we increased the max value because every time we split a mesh, we have one more mesh to process. We also have to pass a progression pointer to the FBX context, which will be saved to a member variable. And I'll add an accessor function for it as well. In import FBX function, which is called from the editor, we now need a function pointer to a callback function. Effectively, we'll be calling our C# code from C++. We can construct a local instance of progression, passing it the callback function pointer. We pass a pointer to this local instance, to FBX context, and to process scene function. When reading FBX meshes, we increase progress maximum every time we read a new mesh. One more function that calls process scene is the create primitive mesh function. However, this time we don't have multiple meshes to process, so we can pass a pointer to a default progression instance. By the way, we don't need to set this explicitly anymore, so it can be removed. Oops, I forgot to actually set this member variable. Good catch, Visual Studio. This is everything we need to do in the C++ side. Now we have to pass the function pointer from the editor. The way we create a function pointer type in C# is by using a delegate. This line defines a function pointer type that takes two signed integers. Note that this is the same as the progress callback type we defined in C++. Well, let me rename it to progress callback. When importing an FBX file, we get the corresponding importing item from the collection, and if it exists, we can create a function pointer to its setProgress method. Note that setProgress has the same signature as progress callback delegate. Finally, we pass our delegate to the native import FBX function. And that's all we need to do for getting import progression. Let's try it out. Well, I can see it works, but you probably can't, and that's because the text is still black. So I need to set the font color. Let me try and create a local style for text blocks. For some reason, even setting a local style doesn't get picked up by our text blocks. I guess I'll have to explicitly set the font color then. Okay, now we can see that this item had 3 meshes. Let's try another one. This model's got 4 submeshes. Notice how quickly they get processed compared to the time it takes to just read them using FBX SDK? It makes me cringe every time. Now let me show you what happens when I import the famous Sponza scene. I'll make a folder for it and drop the FBX file containing the scene. Let's just hit import and we see right away that it has more than 400 submeshes. And as you can see, each submesh has been saved to a separate asset file. This is because the meshes weren't grouped or parented in any way, and therefore were considered as separate objects by the importer. Although this is technically correct, it would be gravely inconvenient to add them to the game scene, set materials, or do any kind of scene organizing with them. In this case, we would like to just have a way of coalescing these into a single asset file, and that's exactly the next bit of this video. We already added the UI setting for this in one of the previous videos, so now we only have to handle the case when it's checked. In order to coalesce meshes, we simply need to write a new function that, well, coalesces all meshes that we found in an FBX file. This function is called after we have all the data that define an LOD group, but before processing meshes to the final data format. Here we pass the LOD group that contains an array of meshes to be coalesced, and it will yield a single mesh. We also pass a progression pointer. Sometimes it's not possible to coalesce meshes. The function will return true if it succeeded in doing so. We start by copying some information to the combined mesh. I decided that it will have the same name as the first mesh in the array. We also have to determine the elements type, which depends on what data are present in the first mesh. I'll update this function a bit such that it returns the elements type instead of modifying the mesh directly. Of course, we have to write this value to elements type member variable where we call this function. Next, we copy the LOD threshold and LOD ID. We also resize the array of UV sets to have the same size as the first mesh. Now we have to determine if the array of meshes can be combined into a single mesh. In Primal Engine, this is only possible if all meshes have the same vertex format, the same number of UV sets, belong to the same LOD, and have the same LOD threshold. Although I'm not entirely sure about the last one, but we'll see. We'll return false if any of these are not the same. If everything matches, then we can proceed with combining meshes. This will involve appending vectors that contain various data. I'm going to write a function that makes it easier for us to do this. It will take a source vector and append it to the destination vector. Here, the POD part of the function name stands for plain old data, which indicates that this function is intended to work with data types that don't need any non-trivial kind of construction, destruction, or copy operation. This is because we are going to use memcopy, which simply copies an array of bytes from one memory location to another. So we just resize the destination vector such that it has enough room to contain both vectors, and then we copy the data from source to the location past the end of the destination vector. Note that the vector class from the standard library does this the right way by calling move or copy constructors, move or copy assignment operators, and destructors, which is slow AF. It might get optimized by the compiler, but I'd rather not depend on the whims of the compiler in this case, since I already know I'm working with simple data types. Now we can call this function to append positions, normals, tangents, and color data. Note that nothing will happen if any of these arrays are empty. For the UVs, we have to copy each UV set. Right now we only support one UV set per mesh, but I'll do it like this in case we'll support multiple UV sets sometime later. Next, we append material indices and the array of raw indices. Because the index of each vertex that was appended is now different, we have to update all indices so that they point to the right vertex. This is done easily by adding to each index the vertex count of the mesh before appending the new one. Last step is to construct an array of distinct material indices. We need this in order to split meshes that use a different material. So if combining meshes was successful, some submeshes could be split again later since we can't render a mesh using multiple materials. At the end, we return true. Now we are ready to call this function, which happens in getScene if the coalesce meshes setting is on. Of course, we need to add this setting first. So if this setting is not true, we proceed as before, which is, we go through the node hierarchy in the FBX file and try to get all meshes attached to its child nodes. If there are any meshes, we'll add the LOD group to our scene data. However, if the user wants to coalesce meshes, instead of putting these meshes in separate LOD groups, we'll put everything in a single LOD group. Then we call coalesce meshes in order to try and combine them, and if that succeeded, we'll replace everything with a combined mesh and add the resulting LOD group to the scene data. This should take care of combining meshes. Before going back to the editor and test it, I'd like to do a tiny bit of code cleanup in our C++ code, which is mostly adding the const keyword where we would like our variables to be read-only. Okay, that was all. Let's go back to the geometry class and add a new import setting for coalescing meshes. We already added this setting in Content Tools API, so we only need to initialize it and make sure that it's converted correctly from the settings of the geometry class. In addition, we have to include it with the other settings when we save the geometry asset to a file or read it from a file. Don't forget to delete and re-import your already imported geometry assets, since we changed the data format here. Now we can bind the UI checkbox to the new property that we just added. Oh, I see. Data already returns a pointer to the start of the array, so we don't need to take its address again. And I forgot to use the progression. When we combine meshes, we need to decrease the number of items, since now we have fewer meshes to process. So max value for progression should go down. We should be careful not to subtract from max value when it's 0, because since it's an unsigned integer, it would wrap around its value. So we subtract 1 if max value is larger than 1. Otherwise it remains 1. As I mentioned, we have to delete already imported geometry assets. I wish I had created those settings as bits in a 32-bit flag, so the format wouldn't change every time we add a new setting. We can still do that, of course, so maybe I will at some point, who knows. Okay, let's create a folder for the Sponza scene again and import it with Coalesce Meshes setting turned on. We are running in debug build, so it's a bit slower, but it should decrease the number of items after it's done reading them. Any minute now. Okay, that didn't work, but let's see if the actual combining of meshes succeeded. And that worked perfectly. We can see here a geometry asset with 2 submeshes. Apparently the FBX nodes used 2 materials which caused the combined mesh to be split in 2 submeshes. So these vases and the lion ornament seem to have a different material than the rest of the scene. Okay, cool. Now let me fix the issue with progression values. We need to use the progression member variable instead of a local variable. Now it should work. Let's try again in the release build. Well, that went rather fast, but it worked. Although it looks like it's off by 1, but I'm not sure I care enough to try and figure this out right now since we are running a bit late. But I'll probably go in and fix it in the next episode. Let's actually try and see if that always happens. This robot model has 5 submeshes, and we can see this time it resulted in a single mesh. And like I said, without coalescing meshes, it has 5 submeshes. So that looks about right. And finally, the Jane model can't be combined because it uses different vertex formats. Although I'm not sure if this one is entirely correct, but we'll see if I can come up with a fix in the next one. Anyway, this completes everything I wanted to do for geometry import settings configuration. In doing this, we also added a lot of infrastructure, which we don't have to do again when we add the texture import settings configuration. Speaking of which, that's what we are going to start working on in the next episode. I hope you enjoyed watching this video and that there was something new in here that you could use in your own projects. Thank you as always for joining me, and I'll see you next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub, so you don't have to type everything over from the video. Plus there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering.